Imagine a world where nobody knew why an apple fell to the ground, what the stars were made of, or what electricity really was. Thousands of years ago, humans looked at the sky and began asking one of the biggest questions ever. How does the universe work? From the ancient philosophers of Greece to Newton's laws of gravity, from Einstein's strange ideas about space and time to the mysterious world of quantum mechanics, physics has completely transformed our understanding of reality. Scientists discovered invisible forces, explored the structure of atoms, unlocked the secrets of light, and eventually learned to detect ripples traveling through space-time itself. This is the extraordinary story of physics, from the first questions about nature to the deepest mysteries of the universe. Physics began with simple questions. Ancient people wondered why objects fell, why the sun moved across the sky, and what everything around them was made of. These questions marked the beginning of humanity's attempt to understand nature. In ancient Greece, philosophers began explaining nature through reason and observation rather than relying only on myths. They discussed motion, matter, time, space, and the structure of the universe. Aristotle became one of the most influential thinkers of the ancient world. He developed theories about motion, matter, forces, and the heavens that influenced scientific thinking for centuries. Aristotle believed that objects naturally move toward their proper places. Although many of his ideas were eventually proven incorrect, his organized approach to studying nature was highly influential. Archimedes of Syracuse approached physical problems using mathematics. He studied levers, floating objects, fluids, geometry, and mechanical systems. Archimedes developed important ideas about buoyancy. His work showed that mathematical reasoning could be used to understand how objects behave in water and other fluids. Ancient philosophers also debated what matter was made of. Some believed everything consisted of elements such as earth, water, air, and fire, while others imagined tiny indivisible particles. Astronomy was another important part of ancient physics. Observers carefully tracked the movements of the sun, moon, planets, and stars. Ancient physics lacked modern instruments, precise measurements, and controlled experiments. Still, these early thinkers created many of the questions that later scientists would answer. The ancient world did not yet understand gravity, atoms, electricity, or the true structure of the universe. But it had taken the first important step, asking how nature works. After centuries of relying heavily on ancient ideas, Europe entered a period of major scientific change. The Renaissance encouraged scholars to question traditional explanations. Nicolaus Copernicus proposed a revolutionary idea. Earth was not the center of the universe. Instead, Earth and the other planets traveled around the sun. Copernicus's idea challenged a worldview that had dominated European thought for centuries. It changed humanity's understanding of its position in the cosmos. Galileo Galilei used a telescope to examine the heavens. He observed mountains on the moon, phases of Venus, and moons orbiting Jupiter. Galileo also studied motion. His experiments showed that physical motion could be investigated through measurement and mathematics. Johannes Kepler carefully analyzed planetary observations. He discovered that planets travel around the sun in elliptical orbits rather than perfect circles. Kepler's discoveries demonstrated that mathematical laws could accurately describe the movement of planets across the sky. The scientific revolution changed the process of discovering knowledge. Observation, experimentation, measurement, and mathematics became increasingly important. The discoveries of Copernicus, Galileo, and Kepler gradually weakened the dominance of ancient explanations of nature. Their work prepared the way for Isaac Newton, who would unite the mathematics of motion with the physics of gravity. Isaac Newton became one of the most important scientists in history. His work transformed the study of motion, forces, gravity, light, and mathematics. Newton developed 3 laws of motion that explained how objects behave when forces act upon them. His first law introduced the idea of inertia. Objects tend to remain at rest or continue moving unless an external force changes their motion. Newton's second law connected force, mass, and acceleration. This relationship became fundamental to classical mechanics. His third law explained that forces occur in interacting pairs. When one object exerts a force on another, the second object exerts an opposing force. Newton also developed the theory of universal gravitation. He proposed that every object with mass attracts other objects through gravity. Gravity could now explain both an apple falling toward Earth and the Moon remaining in orbit around Earth. In 1687, Newton published Principia Mathematica. The book presented his mathematical laws of motion and universal gravitation. Newton also studied light. His prism experiments showed that white light could be separated into a spectrum of different colors. Newtonian physics became incredibly successful and remained dominant for centuries. Yet eventually, scientists would discover phenomena that required a completely new understanding of nature. During the 18th century, scientists became increasingly interested in electricity. Strange electrical effects could be produced and studied in laboratories. Scientists gradually discovered that electricity and magnetism were connected. This connection opened an entirely new field of physics. Michael Faraday became one of the most important experimental scientists of the 19th century. His work transformed understanding of electromagnetism. Faraday discovered electromagnetic induction, showing that changing magnetic fields could produce electric currents. This discovery became a foundation for electric generators. Mechanical motion could be transformed into electrical energy. Faraday also developed the concept of fields. He imagined invisible lines of influence surrounding magnets and electrical systems. James Clerk Maxwell later expressed Faraday's ideas mathematically. His equations unified electricity and magnetism. Maxwell's theory predicted electromagnetic waves traveling through space. This was a remarkable connection between electricity, magnetism, and light. Light itself was understood as an electromagnetic wave. This showed that apparently different areas of physics could actually be connected. By the end of the 19th century, classical physics seemed extremely powerful. But strange experimental results were beginning to reveal that a deeper revolution was coming. At the beginning of the 20th century, Albert Einstein challenged some of the deepest assumptions in physics. Einstein's special theory of relativity changed how scientists understood space and time. They were no longer completely separate and absolute concepts. Special relativity showed that measurements of time and space can depend on the relative motion of observers. The theory also established the constant speed of light in a vacuum as a fundamental feature of nature. Einstein's famous equation E equals mc revealed a deep relationship between mass and energy. Einstein later developed general relativity, a new theory of gravity. In this theory, gravity is connected to the curvature of spacetime. Massive objects can distort spacetime around them. Other objects then move through this curved geometry. General relativity predicted phenomena such as the bending of light by gravity and the existence of black holes. Einstein's theories completely transformed humanity's understanding of the universe. Space, time, matter, energy, and gravity became deeply connected. But while relativity explained the universe on enormous scales, scientists were discovering that the microscopic world followed an entirely different set of rules. Quantum mechanics emerged when scientists discovered that atoms and particles behaved in ways that classical physics could not explain. Max Planck helped begin the quantum revolution by proposing that energy could be exchanged in discrete amounts called quanta. Niels Bohr applied quantum ideas to atoms. He proposed that electrons could occupy specific energy levels. Werner Heisenberg developed a major mathematical approach to quantum mechanics and introduced the uncertainty principle. The uncertainty principle showed that certain pairs of physical properties cannot both be known with unlimited precision at the same time. Erwin Schrödinger developed another formulation of quantum mechanics. His famous equation describes how quantum states change over time. Quantum mechanics showed that particles can display wave-like behavior. The microscopic world was far stranger than everyday experience suggested. Instead of always predicting exactly what a particle will do, quantum mechanics often predicts probabilities for different possible outcomes. Quantum theory successfully explained atomic behavior and became the foundation of many technologies, including lasers and computer chips. Quantum mechanics became one of the most successful theories in science, but its strange behavior continues to raise profound questions about the nature of reality. The discovery of the atomic nucleus revealed that atoms were not indivisible. At their center was a tiny, dense nucleus. Ernest Rutherford's famous experiments provided evidence for the nucleus and showed that most of an atom is empty space. Scientists later discovered that nuclei contain protons and neutrons. Understanding these particles became a major goal of nuclear physics. Scientists also discovered radioactivity, in which unstable atomic nuclei naturally transform and release radiation. Nuclear fission revealed that heavy atomic nuclei could split into smaller nuclei while releasing large amounts of energy. During the Second World War, scientists working on the Manhattan Project developed the first nuclear weapons, beginning the atomic age. The nuclear age demonstrated the enormous energy stored inside atomic nuclei and changed science, technology, and world history. After the war, scientists developed peaceful uses of nuclear technology. Nuclear reactors could produce heat and generate electricity through controlled fission. Nuclear physics also became valuable in medicine and scientific research. Radioactive materials and nuclear techniques have been used in imaging and certain medical treatments. The study of nuclei eventually led scientists deeper into the structure of matter, toward quarks, fundamental particles, and the modern Standard Model. Modern physics attempts to understand nature at every scale, from the smallest known particles to enormous galaxies and the structure of the universe itself. Quantum field theory became a major framework for describing fundamental particles and their interactions. The Standard Model describes many of the fundamental particles and interactions known to physics with extraordinary accuracy. The discovery of the Higgs boson in 2012 provided important evidence for the Higgs mechanism associated with the origin of mass for fundamental particles. Yet modern physics still has a major problem. Gravity does not fit naturally into the Standard Model of particle physics. Black holes remain among the most fascinating objects in the universe. Their extreme gravity creates enormous curvature of spacetime. Gravitational waves gave scientists a completely new way to observe the universe. These tiny ripples in spacetime can be produced by violent cosmic events. Dark matter is another major mystery. Its existence is inferred from gravitational effects, but scientists still do not know exactly what it is made of. Dark energy presents an even deeper mystery. Observations show that the expansion of the universe is accelerating, but the cause remains unknown. Physics continues to search for answers to the universe's deepest questions. The journey that began with ancient philosophers has now reached quantum fields, black holes, gravitational waves, dark matter, and the earliest universe. We went from wondering why objects fall to detecting ripples in spacetime and studying particles smaller than an atom. But physics has one fascinating problem. The biggest questions are still unanswered. What is dark matter? What happened before the Big Bang? And can quantum mechanics and gravity ever become one theory?